Let's go ahead and do a Beer's law calculation. Take a moment, read this problem, I'll read it with you, and then we'll think through the problem together. A red solution has a concentration of 23.5 micromolarity and a measured absorbance of 0.636 at a wavelength of 592 nanometers. What is the molar absorptivity? Take a moment, think about it. Break down the problem. Pause the video. Okay, let's go ahead and think about the important things that are inside the problem. We'll see what information we have that we need to solve this. We're going to start by recognizing that as soon as we have concentration and absorbance, we are probably looking at a Beer's law problem. So as soon as we see those two things, that gives our mind a hint that says, oh, I'm probably going to be doing this equation from the equation sheet from the textbook, or absorption and concentration are related to each other. We also have a given concentration and a given absorbance. So we already have two of our variables defined. We can also see that we have what is the molar absorptivity. So it's clearly asking us to find epsilon. You'll notice I didn't underline the 592. That is because this number is actually not necessary for doing the calculation. This is necessary for part of defining epsilon, but not used in calculation. Ooh, that's bad writing. Let's fix that. Defining epsilon, but not used. Right? So that is the same as saying, you know, this word red is not going to be used in the calculation. It's important for defining the epsilon, kind of the chemical compound and the wavelength of observation, but it's not going to play a role in the calculation. So let's go ahead and start plugging in the parts we know and solving this. We've got 0.636 for our absorbance. You'll notice absorbance has no units because absorbance is a ratio of intensities. It ends up with no units. Epsilon is what we're looking for. We're not given a p-value. We're not given a path length. One of the most common mistakes people make is they try to use the wavelength in for the path length. However, those are very different things. The path length is how far the light needs to travel inside the sample. The wavelength is a property of the light. For almost all of our calculations in this class, we can assume that the path length is going to be 1 centimeter. That's because we're almost always going to be using our standard cuvettes. On quizzes and exams, we should specify what the path length is, but if it's ever a question, you can ask, but it's most likely going to be 1 centimeter. And then we've got our concentration. Our concentration is going to be 23.5 micromolarity. And I'm going to go ahead and just convert that really quick using our unit conversion rules for prefixes, remembering that micro is 1 times 10 to the minus 6, and that molarity is moles per a liter. I'm going to take this, I'm going to plug that in for that micromolar, and we'll have 23.5 times 10 to the minus 6 moles per a liter. After we have that part put together for solving a Beer's law problem, it's just doing the calculation. I'm going to do 0.636 divided by 1 centimeter times 23.5 times 10 to the minus 6 moles per liter. And that's going to give us our value for epsilon. I forgot to pre-calculate this, so I've got to punch it into my calculator real quick. You can go ahead and do the same thing. 0.636 divided by 23.5. Oh, important thing I will make note of as I punch this into my calculator, make sure you are careful with your parentheses when you're doing divisions in your calculator. Depending on how your calculator has it set up, you want to make sure that you're not accidentally dividing by 23.5 and then multiplying by 10 to the minus 6. So watch out for that. I received a value, a numerical value, 27,063, 123, and the units would be, let me make sure I got my units right. I'm going to have centimeters and moles on the bottom. I'm going to have, we can do it like this, centimeters minus 1, molarity minus 1. That's a fine unit for this. So this would be my answer for the molar absorptivity. For most dyes and solutions, we should have an expected epsilon value somewhere between 10,000 and 100,000. A little bit bigger, a little bit smaller is okay, but if we're doing it in units of molarity, notice I converted to moles per liter, that's molarity, this will give us a value, if we're in these units for typical dyes, somewhere between 10,000 and 100,000. You could have also, using the units that we converted to, you could have done this as centimeter minus 1 liters per a mole, getting the inverse of that since it's on bottom of the fraction. This is a pretty straightforward Beer's Law problem, so let's go ahead and try a problem that's a little bit more complicated. Again, take a moment, read the problem, think through it. This one's going to take a couple steps. The absorbance of a 35 milliliter blue solution at 10.6 micromolarity is 0.725 at a lambda max wavelength of observation of 636 nanometers. What is the absorbance when 10 milliliters of water is added? If you haven't paused the video, pause the video. Take a moment, work on the problem before we get to the solution. Again, we'll notice we've got absorbance, we've got concentration, so we're looking at Beer's Law again. A equals epsilon BC. In this case, though, we've got a solution and then we're adding water to it. So we also in this case have a dilution happening. So in this case, we've actually got kind of two separate problems. And this is going to be similar to what we did before. You'll notice, because we have the concentration and the absorbance, assuming a path length of 1, we can solve for epsilon from this first set of information. And then we can solve for the concentration in the second set of information to find the new absorbance. And that's essentially what we're looking for. One of the most important things when we're doing a problem is identifying what we're actually looking for. So we're looking for a new absorbance after we add water. Logically, we can already stop and think before we jump to our calculator or anything. We can say, okay, because of the linear relationship between absorbance and concentration, we know that adding water, which is diluting our solution, should drop the concentration, which means our absorption should also drop. We should get a number that is smaller than 0.725. Because our concentration is going down with the added water, the absorbance should also go down. And it should go down proportionally. So I can already look at this and say, I'm increasing the total volume by about a third, by about 30%. So I should see this go down by about a third. I'm going to guess my answer is going to be somewhere around 0.5. Let's do the math and see what the actual answer is. I'm going to start with doing part 1, calculating out what the molar absorptivity for this blue material is. 0.725. This is very similar to the problem we just did. It's equal to epsilon times 1 times 10.6 times 10 to the minus 6. Notice I'm getting a little, let's not be too sloppy with our units. We should be careful. That's a centimeter there. I was getting a little sloppy. go ahead and calculate epsilon out. We're going to have epsilon is equal to 0.725 divided by 1 times 10.6 times 10 to the minus 6. Molarity, again, I forgot my centimeter. Calculating 0.725 divided by 10.6 times 10 to the minus 6. That gets me a value for this particular blue dye at this particular wavelength. I get a value of 68,396 centimeters minus 1, molarity minus 1. I can then go ahead and say, with this, I can start thinking about part 2 of this problem, where now the absorbance is the question. I know the epsilon from above. I know the path length, and I can calculate the concentration. So I want to figure out the absorbance. That's the thing we're looking for. I know the epsilon, that's just that right there. I know the path length is going to be 1, and I can calculate the concentration from this M1V1 calculation. So let's go ahead and do that. To get the concentration, I'm going to say we've got 35 milliliters of our original 10.6 solution. Again, units. You can tell I haven't done this in a few weeks. Milliliters times 10.6 micromolarity is equal to total volume at this point is going to be 45 milliliters times my new molarity. Now, it is safer, of course, to convert the milliliters to liters, do your multiplication so you've got your number of moles equal to your number of moles. But in this case, we can go ahead and just divide over the 45 divided by 35. Notice the milliliters will cancel the milliliters, and my answer will be in units of micromolar. So, doing the math here, I'll have 35 divided by 45. If you want to convert to liters, that's times 10 to the minus 3 liters, times 10 to the minus 3 liters. Notice the times 10 to the minus 3 is going to cancel out. Times 10.6 micromolarity. That's going to give us our new concentration, which is just going to be slightly less. I think my estimation was off. 35 divided by 45. Ooh, calculator's acting weird. There we go. 35 divided by 45 times 10.6. 8.24 micromolarity. Almost there. Again, this equation works, this M1V1, M2V2 equation works when we're only adding water, when we're not changing the number of moles, right? The number of moles is the same, but the concentration and the volume are changing. With this, I can now go ahead and say absorbance is equal to the epsilon value, 68396, times the path length of 1, times the concentration, being careful, molarity, micromolarity. I have to make sure I do that conversion. 8.24 times 10 to the minus 6 molarity. Make sure you can still see that. Ooh, off the screen a little bit. That is going to give us absorbance, 8.244. Sorry, let me type that in. 8.24 times 10 to the minus 6, being careful with parentheses, times 68396 times 1. Oh, that wasn't that far off. 0.563 for the absorbance. Again, no units on the absorbance. Notice in this problem, we were able to combine two separate ideas, the idea of dilution and the idea of absorbance into one problem. A little bit more complicated, but still simple ideas put together.